in this video we are going to study about the slenderness ratio, how it is calculated, on what factors the slenderness ratio depends. So first of all, slenderness ratio. Slenderness ratio is the ratio of effective length of a member to the radius of gyration of the section. The slenderness ratio depends on the three parameters: effective length factor, unbraced length, and radius of gyration. So these are the three factors on which the slenderness ratio depends. Effective length factor K, which depends on the end condition and end condition of the column. So this K factor, this depends upon the end condition of the column. The second one is unbraced length of the column in the direction or in strong direction or in weak direction, whichever gives the more answer for KL over R. And the third parameter is radius of gyration, so which may be Rx, Ry, strong and weak direction, for uniaxially and biaxially symmetrical cross sections, and least radius of gyration RZ for unsymmetrical cross section. So this L and radius of gyration, we need to consider these factors K, Lu and R, the corresponding value for which we are going to consider. And if we want to get the maximum slenderness ratio, then we need to consider the minimum radius of gyration and maximum effective length or unbraced length to get the maximum value of slenderness ratio. One by one we will discuss all these parameters, what are these and how we can calculate these parameters. So first of all, unbraced length. It is the length of column between two consecutive supports or braces denoted by Lux, Luy in the X or Y direction respectively. So if we have a support here and a support here, so this is unbraced length Lu. But if we have bracing in between like this, so in that case this much will be the Lu, unbraced length. A different value of unsupported length may exist in different direction and must be used to calculate the corresponding slenderness ratio. So first we need to consider the direction. For example, if we have a W section, so if we are going to consider this axis, for example this x-axis, so we need to consider the length corresponding to this. If there exists bracing in this direction at the intermediate point, so then we need to consider the distance from the support up to that bracing. Otherwise we need to consider the whole length. But if the bracing is in this direction, there is no bracing in this direction, then we will consider this unsupported length from the first support up to the last support. So we need to consider the corresponding direction, calculate or to select the unsupported length value. So to calculate the unsupported length of a column in a particular direction, only the corresponding supports and braces are to be considered, neglecting bracing, preventing buckling in other directions. So as I have told earlier, that if we are considering this axis, x-axis, but the bracing is also present in this direction at some intermediate point, so then we will not consider this bracing, because if we are considering this axis and we are going to calculate the slenderness ratio about this axis, then we need to consider the bracing about this axis or in the direction perpendicular to that axis, because this bracing in the perpendicular direction will divide the unsupported length. So then we need to consider the unsupported length from support up to that bracing. Okay, next is effective length of a column. So the length of the column corresponding to 1/2 sine wave or buckle shape, 1/2 sine wave of the buckle shape, or the length between the two consecutive inflection point or supports after buckling is called effective length. So for example, we have a pin support over here and a pin support over here, and this is our column, and it will buckle in this direction from this support up to this support. So here we have a single half sine wave. So this is a complete half sine wave. So this portion is half sine wave. So in that case we have single half sine wave, so this much length will be effective length, Le. But if we have fixed supports at top and bottom, so in that case our failure mode will be like this. So here we have this much half sine wave, so the distance between the inflection point. So this is 1/2 sine wave, and this one will be 1/2 of half sine wave. So this half sine wave is actually the effective length. So the length of column corresponding to 1/2 sine wave of the buckle shape, or the length between the two consecutive inflection point. So here we have one inflection point and the second inflection point. So this is Le. So the next factor is effective length factor. So to calculate the effective length, we need effective length factor from the unsupported length. When we want to calculate the effective length from the unsupported length, then we multiply it with the effective length factor. So actually this effective length factor is the ratio of length of one half sine wave of deflected shape after buckling to the full unsupported length of the column. So this unsupported length factor, or this effective length factor, LE is equal to LE over LU, effective length divided by unsupported length, or we can write that LE is equal to K time LU. This effective length is equal to effective length factor multiplied by the unsupported length. So this depends on the end condition. So this K value depends on the end conditions and the fact that whether side sway is permitted or not, whether the side sway is permitted in the column or in the building or in the frame or not. So what is side sway? I have uploaded a video related to the side sway, so you can see that video, that whether the side sway will exist in the building or not, and what is side sway, how it is prevented. So you can follow that video, or you can watch that video to understand what is side sway. Greater the K value, greater is the effective length and slenderness ratio, and hence smaller is the buckling load. So this point need to be understood. So when the K value is greater, so the effective length will be larger. So when effective length is larger, then the ratio KL over R, that will be larger. So for larger slenderness ratio, the load or the buckling load will be smaller. So the column or the section will buckle at the smaller loads. The next is how we can calculate this effective length factor K. So we have a simple expression, K is equal to 1 over N, and N is number of half sine waves. So K value in case of no side sway is between 0.5 and 1, but when there is a appreciable side sway, its value can be equal to 1 or greater than 1. So this need to be understood, that when there is no side sway, its value will be from 0.5 to 1, but if there is side sway, its value will be from 1 or greater than 1. So for example, if we first see this condition, this D condition, so we have different types of sports. This is fixed sport, this is pin sport, and this is sport in which rotation is fixed but translation is free, mean it can sway, and the last one is rotation as well as translation, both are free. So here if we see this D case, so here we have pin sport at the top and pin sport at the bottom. So when this column will buckle, so there will form only a single half sine wave. So we will have N is equal to 1, so K will be equal to 1 over 1 is equal to 1. So our K value will be equal to 1 in that case when we have pin sport at the end. But if we have fixed sport at the end, so in that case we have 1 half sine wave, this is 1 half sine wave, and we have quarter half sine wave here and quarter half sine wave here, or sorry, half of half sine wave. So we have 1 by 2 plus 1 plus 1 by 2 half sine wave, mean N is equal to 2. So when N is equal to 2, K is equal to 1 over 2, 0.5. So K will be 0.5, we can see over here. Similarly, if we see the second case, and at top we have a pin sport and at the bottom we have a fixed sport. So we have a sine wave starting from here up to this point. So 1 half sine wave this one, and this will be 1 by 2 of sine wave, half sine wave. So N is equal to 1 plus 1 by 2. So it is 1.5. So K will be equal to 1 over 1.5. So when we divide, so it will become 1 divided by 1.5, 0.667, or we can say it is equal to 0.7. Similarly, in this case we have a port at the top in which the rotation is fixed but translation is free, and at the bottom we have a fixed port. So in that case we have this quarter half sine wave, and then again half of half sine wave, and then half sine wave. So this is 1 by 2 of half sine wave, and this is also 1 by 2 of half sine wave. So N is equal to 1 by 2 plus 1 by 2 is equal to 1. So K will be equal to 1 over 1 is equal to 1. So we can see here the K value is 1. So if we see the next case, E case, so we have a fixed port at the bottom but the top is free. So here in this case we have only 1 by 2 of half sine wave. So N is equal to 1 by 2. So K will be equal to 1 over 1 by 2 or equal to 2. So here we can see the K value is 2. And in the last case we have pin support at the bottom and we have a support at the top which is in which the rotation is fixed but translation is free. So the curvature will be like this. So this is again a half of half sine wave. So n is equal to 1 by 2. So K will be equal to 2. So we can see over here K value is 2. So this is the way how we can calculate this effective length factor K when we have defined end conditions. Mean either it is fully pinned or fully fixed. But in the case when the supports are not predefined, mean it is partially fixed, partially restrained, so in that case the scenario will be different. So if we have partially restrained columns, mean at the end the columns are partially restrained. In case of frame structure we have columns like this. Here we have beams and then beams. So in that case this point cannot be fully fixed. So there will be partial fixity at this position. So in that case we need to calculate or we need to use these charts to calculate the K value. So this is the first chart is for the frames in which sway is prohibited or sway is restrained. So in that case we can use this chart, and in case of frames where side sway is permitted, so in that case we will use this chart. So to find the value of K from this chart we need to calculate GA and GB. GA will be at this joint and GB will be at the bottom joint, and then we need to align these values. This is the alignment chart. So for example we have a GA value 2 and GB value 0.4. So we will join these 2 points with the help of a straight line, and the point at which this line intersect this intermediate scale which is corresponding to K, so that will give us the K value. So here we see its value will be 0.75. So K will be 0.75 in this case. So in the similar manner we can calculate the value for this chart. So the point where this line intersect the K bar or K scale, so the corresponding value can be considered as a K value. So the question is how we can calculate this GA and GB. So GA or GB is actually the ratio of flexural stiffness of columns and flexural stiffness of beam joining at the joint. So for example if we see this joint A, so here at this point we have 2 beams and 2 columns meeting at that joint A. So we need to calculate the flexural stiffness of these 2 columns, the upper one and the lower one, and we also need to find the flexural stiffness of this beam as well as this beam, and then we need to take the ratio. Mean for example this column is C1, C2, this is B1 and this is B2. So G will be equal to flexural stiffness of C1 plus flexural stiffness of C2 divided by flexural stiffness of B1 plus flexural stiffness of B2, and this flexural stiffness is equal to EI over L. So we need to find the EI over L value for all these beams and columns meeting at that point. So we can calculate this G value at point A and at point B. Once we have these G values, then we can easily calculate the K value, or we can easily find the K value from those alignment charts. Okay, so K value for truss or braced frame members. So in case of truss members, the K value can be considered equal to 1, because in case of trusses we assume that our connections are pinned connections. So we consider the pin connection at the end of the member. So in that case we will have a curvature like this. So N will be equal to 1 and K will also be equal to 1. And in case of braced frame we can also consider its value equal to 1. So here we have models that when we can consider the K value 1 or more than 1, or how we idealize the frame. So if we see the first case, we have all the pin supports, but at this point this is braced. It means there is no side sway. Side sway is restrained in this frame, but we have pin support at the top. So here if we see this column, so this column at the top we have pin support and at the bottom we have pin support. So there will be single curvature. We will have N is equal to 1. So the K value will be equal to 1. And if we see this second case, so here we have fixed support at the bottom, pin support at the joints between the frame elements, but the frame is restrained against the side sway. So we have pin support at the top and fixed support at the bottom. So we can idealize this case, and in that case the K value will be equal to 0.85. But if we have fixed support at the bottom, our frame is high Z and the top connections are pinned, but there is no bracing. So in that case we can idealize it in this way. So there will be sway in the outward direction. So here we have 1 by 2 of half sine waves, so k will be equal to 1 over 1 by 2 equal to 2. Similarly, if we have a frame in which the beam is rigid, so when the beam is rigid and the side sway is also prevented by using bracing, so in that case we will have fixed support at the top as well as fixed support at the bottom. So in that case the scenario will be this one, we will have 0.7 value of k. If we have a frame like this, that the beam is rigid and the side sway is not permitted, so in that case there will be no rotation but translation will be allowed. So at the bottom we have fixed support, so translation as well as rotation is prohibited. So we have two half sine waves, so half of half sine wave. So this is 1 by 2 half sine wave and this will be 1 by 2 half sine wave. So n will be equal to 1 by 2 plus 1 by 2. So it is equal to 1 and k will also be equal to 1. So in this way we can idealize these frames and we can calculate the k value.